Well, this is 9th lecture in the series of mechanics of metal forming. We are going to cover the state of stresses topic here and related issues including problems. Basically, this topic may continue up to 2 lectures or 3 lectures, something like that. We are concerned so far the tensor part, tensor representation of a scalar quantity, a vector quantity or a tensor has already been explained how it can be represented in a very compact manner. Now the major topic which concern mechanics part of metal forming is stresses. As you know, stresses, so far whatever we have studied, stress is a vector quantity, but stress in fact it has more than 2 dimension and it has more than 6 component. So let us see this very important topic. So stress at a point. What do we mean by stress at a point? Let us take this particular figure number 1, where you have a, say, if you take an elementary force which is acting on an area, very small area, let the area be delta A of a given body, basically a solid body, and let this elementary force be delta F be represented. So the stress, how do we define stress? So stress acting on this elementary infinitesimal area delta A in the direction of the force delta F can be defined as limit when delta A tends to 0. That means that this area is infinitesimally small, very small, then it is defined that within this infinitesimal area delta A tending to 0, it is defined as delta F by delta A. So now if you resolve this delta force, which delta F force which is in 3 dimensional space anywhere, if it is resolved in 3 basic directions which is perpendicular to the 3 major axes, if it is taken as x, y, z. So if it is resolved in the direction of x as delta Fx, in direction of y as delta Fy, and in direction of Fz as delta F delta Z. So one can say that these directions of the component of the force delta F along OX, OY and OZ directions which is in the plane of delta A. Now if the force component along these directions are taken as, say, as I told, delta Fx, delta Fy, delta Fz, so the stresses corresponding to these directions can be written as that is the sigma xx is equal to limit delta A tends to 0, so that would be in direction delta Fx, delta delta A. Similarly, we can write down it for uh, uh, sigma xy and sigma zx. So, we can write it. Here we are using delta xx, delta yy or delta xy. It is double subscript. As you recall, you can use it for resolving or identifying the stresses directions, where the first script indicates the direction normal to the plane on which the stress is acting, while the second script identifies the directions in which the stress is acting. So, if we take sigma xx, that means the stress on the plane which is perpendicular to OX and which is acting parallel to the axis OX. Similarly, sigma xy would mean that the stress which is acting on the plane normal to the OX and which is acting parallel to the OY axis. So, this way we can find out the different order of stresses at a given point, and then it becomes necessary to specify the stresses at the given point on three mutually perpendicular planes which are taken parallel to x, y and z axis. So, these stresses can act and it can be specified in the double suffix manner, like your sigma xx, sigma yy, sigma zz, and in the direction normal to the stresses like sigma xy, sigma yx, sigma yz, sigma xz, then sigma zx likewise. And the shear stresses, sometimes the second suffix of the normal stress we can delete later, and instead of writing say sigma xx, we can which is equal to sigma yy or sigma zz, they can also be represented in various represented like sigma x, sigma y, sigma z only. This is for easiness. So far if we look at the tensorial notation, these 9 components, that is xx, yy, zz and the xy, yx and corresponding like that, these 9 components could be simply designated by a one representation like sigma I j, as we represented in the tensorial notation, and say the 3 specified directions can be subscripted at I and j. So, I can take place 1 to 3 and similarly j can take the values as 1 to 3, and so these stresses are called as a tensor. So, at a point if it is denoted the array of these stresses, then it can be denoted as your like sigma I j is equal to an array in the form of matrix. So, that becomes your sigma xx, sigma xy, sigma xz, then sigma y x, sigma yy and sigma yz, and similarly the sigma zx, sigma zy and sigma zz. So, now we can see that we are defining the coordinate in terms of x, y, z, and you can also define these stresses in cylindrical coordinate system, that is r theta z, one can define, or like this one 1 to 3 notation can also be given, like when I is equal to j, the normal stresses can be like sigma xx, sigma yy, sigma zz, and when I and j is not equal to, so that comes to corresponding to the shear stresses as sigma xy, sigma yz, sigma zy, sigma zx, sigma xz, and all those things. So these complementary shear stresses like sigma xy is equal to sigma yz, and similarly stresses like sigma yz and sigma zy are similar. It is a complementary to each other, and therefore it can be simply written as that the sigma ij is equal to sigma ji. So to indicate these stresses in a tensorial form as a symmetric. So these are called as the symmetric tensors. Thus instead of 9 component, these stresses can be represented only which are also independent in 6 component. So this is what the stress tensor basically at a point is defined in 9 component, or important one is 6 components. So let us see in this figure which shows the stress. How do you call the graphically one can draw the stress circle which is acting on a body. So let us take this representation, like where particularly let us take the plane stress case, where now let us take this figure number 2, where we have this particular one, so you can see here the sigma, if you are taking as the plane stress means x direction and y direction, z direction is not shown. So the form of a circle which has come to be known as the stress circle, this will form the basis, and that is very popularly known as the Morse circle. So consider a state of the stress having sigma x, sigma y, and sigma xy as the shear stress under the condition when sigma z and sigma yz and sigma zx are 0, because it is a plane stress. So this representation of 2-dimensional stress field can now be shown it on the xy plane. Now if you rotate this xy axis by say an angle theta, and that changed axis then becomes the x dash y dash, and now if we resolve the forces along the new axis, that is x dash y dash, so this will give you the sigma x prime is equal to, as the resolution one can see, sigma x cos square theta plus sigma y sin square theta plus twice sigma xy sin theta cos theta, and similarly the sigma y prime in the new change coordinate direction, sigma x sin square theta plus sigma y cos square theta minus twice sigma xy sin theta cos theta. So and then the shear component in the change coordinate, that can be written as sigma x prime y prime is equal to minus in the bracket sigma x minus sigma y and sin theta cos theta plus sigma xy cos square theta minus sin square theta. Now if you simplify these 3 equations, that is corresponding to sigma x prime, sigma y prime, and sigma x prime y prime, and if you use the simple trigonometry relationship, we can arrange these equations in this form, which is the equation number 2. So one can see here, and in case if sigma x is represented by say sigma 1 and sigma y is represented by sigma 2 as the principal stresses, and say the sigma xy, that is the shear stress, is 0, then the same equation number 2 can be simplified as sigma x prime is equal to half of sigma 1 plus sigma 2 plus half of the sigma 1 minus sigma 2 cos 2 theta, and similarly the y component on the change, one can see, one can show it in this manner, equation number 3. Now let us see this figure. This Mohr circle for the plane stress can be now written as, where the x corresponds to the direct axis and y axis corresponds to the shear stress. So now if you plot it, see the center C of the circle becomes your sigma x, and similarly corresponding to this one can draw it here. So at a point theta, if the stress at a point which is theta degree to the direct stress plane, so one can represent it in this fashion. So both the stresses on xy plane and when the plane is rotated by theta degree, so it is also shown here in this figure, which is corresponding to delta x prime and delta y prime, one can see. So here you see the stress x prime y prime, which is given by -1/2 sigma 1 minus sigma 2 sine 2 theta, and if we square and add this term from the equation 1, it will give you this particular equation, which is sigma x prime minus half of the sigma x plus sigma y square plus sigma x prime y prime square, and it equals to this one, the right hand side, which is given here. So one can note this one on this side here it is, and it is direct form of the stress on one of the previous plane, and when it is rotated it is equaling here. So this equation of circle, which is circle with normal stress and shear stress, it is on the coordinate axis. So the coordinate axis of center is, if you identify from here, it becomes as 1/2 sigma x sigma y and 0, and its radius would be half of sigma x minus sigma y square plus sigma x y square and under root 2, half whole thing. So in order to consider the circle, let us locate. So how this is being, one can see, you can locate the sigma x and sigma y along the normal axis and locate the center at this one, which you can take it and cut it along the axis. So you can identify the center at half of sigma x plus sigma y, as in this, which is shown. So if the clockwise shear is taken as positive and anti-clockwise is taken as negative, then sigma xy on x axis would be taken as positive shear, and it can be plotted as minus sigma xy along the shear axis from the point representing the sigma x. So similarly one can also sigma xy and along the y plane would be negative, and therefore one can plot like this. So to find the stresses on any plane which is inclined at an angle theta to the plane on which sigma x is normal, you can set off an angle 2 theta from the cx plane to the plane which is located as capital X prime and y prime on the circle to get the sigma x prime, sigma y prime, and similarly the shear part of the x prime on this change axis. By equation number 2 you can utilize, since the principal stress are direct stresses on the planes across which the shearing stress are 0, therefore one can say that the sigma 1 is OA, which is half of the sigma x plus sigma y plus in bracket the sigma x minus sigma y by 2 whole square plus sigma xy whole square under root all of these component. So this is what one can find out from the Mohr circle. Now let us see this particular figure number 4, where we can take a like this 3 axis, we can take it like here, and if we take a plane which is from this center, if you take a plane which cuts 3 axis as the direct stress sigma 1, sigma 2 and sigma 3 axis at a point O on this. So let us see on this particular oblique plane which cuts at point A, capital B and capital C along the 3 axes. So sigma 2, now it is normal. So from this the plane, it is normal here at the point O, say on the so the sigma 2 can be written as if you see here, it can be written as OB, that is the OB, and so it can be written as half of sigma x plus sigma y plus the whole thing in bracket sigma x minus sigma y by 2 whole square plus the shear component on this xy plane, that is the sigma xy square and root of this. So this equation number 5th, the maximum shear stress can be now found out as minus from the one can see from the Morse circle diagram itself, if the maximum shear stress comes out to be your half of sigma 1 minus sigma 2, or it can also be written as the other form, which is including the sigma x minus sigma 2 square plus shear and under root. So this stress circle can be drawn as you have seen easily either with principal stress or the direct stress and shear stress as known on the plane, and the stress on any plane which is inclined to at an angle can be evaluated from the stress circle without going through the solution of the equilibrium equations and all that. So for plane stress of 2-dimensional coordinate have been considered, and similarly one can also draw for the 3-dimensional stress when it is more frequently encountered. So let us consider the situation where it is 3-dimensional. So you have the stresses acting on the body as sigma 1, sigma 2 and sigma 3 as shown in previously in figure number 4. So one can arbitrarily select this particular plane ABC as one. So and let the normal stress be Sn, represented as capital Sn. So resultant of the shear stress can be shown at shear, that is capital SS. So if the direction cosine on the that ON, if you look here ON, it represents on normal to the plane ABC. So if these directions cosines are, let us take as LMN, so the component of the stresses that is S1, S2 and S3 in 3-dimensional space along 1, 2, 3 directions can be simply as S1 as L sigma 1, S2 as L sigma 2 and S3 as N sigma 3. Then one can write down that is this normal stress is equal to LS1 plus MS2 plus NS3, which is in the form of direction cosines, and it can also be represented as L square sigma 1 plus M square sigma 2 plus N square sigma 3, and therefore the stress, the shear stress SS square becomes equal to S1 square plus S2 square plus S3 square minus Sn square, and then it can further be written as if we transpose the Sn square to the left hand side, so it is Sn square plus Ss square becomes equal to L square sigma 1 square plus M square sigma 2 square plus N square sigma 3. And also as we know that the direction cosines, sum of the direction cosines is square is equal to 1. So if we substitute the equation 7, 8 and in 9, this gives the value of L square, M square and N square. So for an example, L square is in the numerator, which is equal to, in the numerator side as SS square plus 2 bracket multiplication of 2 brackets as number 1 bracket as Sn minus sigma 2 and second bracket as sigma n minus sigma 3, and on the denominator side the multiplication of 2 brackets, that is sigma 1 minus sigma 2 and sigma 1 minus sigma 3, and likewise M square and N square can be calculated, and this is what has been given in equation number 10. So therefore one can then write down that Sn minus sigma 2 multiplied by Sn minus sigma 3 plus Ss square, and that becomes equal to L square sigma 1 minus sigma 2 multiplied by sigma 1 minus sigma 3 or sigma n minus sigma 2 plus sigma 3 by 2 whole square plus Ss square, and that is equal to L square multiplied by sigma 1 minus sigma 2 multiplied by sigma 1 minus sigma 3 plus sigma 2 minus sigma 3 by 2 and whole square. That is what is the equation number 11. The above equation specifies a circle and having center as Sn and Ss. The plane with the center, the circle on the plane Sn and Ss, that is the plane is Sn and Ss, and the center of the circle is located at sigma 2 plus sigma 3 by 2 and 0. So similarly one can also write down for the other component, that is sigma 3 and sigma 1 and sigma 1 and sigma 2. So the equation similar to equation number 11 can be written as equation 12 and equation 13, which has been shown here. Please note that these equations are specifying a circle in different planes. For an example, if you see the equation 12, it defines a circle whose center is located at sigma 3 plus sigma 2 sigma 1 by 2 comma 0, and the center of the circle is represented by equation 13 having the center as sigma 1 plus sigma 2 by 2 and 0. So the radii of the circle which is defined by equation 11, 12 and 13 are, therefore it can be written as in bracket having two major components, that is your L square sigma 1 minus sigma 2 multiplied by sigma 1 minus sigma 3 plus sigma 2 minus sigma 3 by 2 whole square, and this is all this in a under root. So if you look at this figure 6, where the static equilibrium on an infinitesimal tetrahedron is shown, and if you locate the center and if it is the points are identified as C1, C2 and C3 here, so it is therefore clear from equation 14 to equation 16 that the admissible values of normal stress, that is Sn and Ss, the shear part, must lie in the shaded area which is bounded by the circles as shown. So these points are to be noted very clearly, and the second thing is to be noted is that stress invariant. So let us see what is stress invariance. Let us consider the sixth component of stress at a point in xyz coordinate system that has been shown here in figure 6, where the equilibrium of the infinitesimal tetrahedron is taken up. So the stresses that is acting on this point can be evaluated by considering the static equilibrium of an infinitesimal tetrahedron formed by the plane ABC, and the three coordinate planes, that is AOB, BOC and AOC are there. Let delta be the area of triangle ABC whose normal has direction cosines as LMN. The area of these coordinate planes, that is AOB, BOC and AOC, are therefore delta L, delta M and delta N respectively. And let capital S be the resultant stress on capital A, capital B, C, this particular element with normal, that is the direct stress, and shear stress component as Sn and Ss, and the components of the stresses having Sx, Xy and Sz along XYZ directions, and this has been shown in figure 7 again. So the equilibrium of the forces on the tetrahedron OABC in x direction can be written as, that means delta Sx, and that is equal to what the component sum of the three components, that is delta L sigma x plus delta M sigma yx plus delta N sigma xz. Look at this figure carefully, 7, where the components has been shown resolved along with the normal and shear component as well. So these component becomes as Sx, and that is equal to L sigma x plus M sigma yz plus N sigma xz. Sy becomes equal to L sigma xy plus M sigma y plus N sigma zy, and Sz becomes equal to L sigma xx plus M sigma yz plus N sigma z. The normal stress, that is Sn on plane ABC, can be therefore evaluated by projecting Sx, Xy and Sz on On. Thus one can write this in as given here in equation 20. That means the normal stress becomes Sn becomes L Sx plus M Sy plus N S y as the components, Sz as the component, and if we substitute the value of Sx, Sy and Sz in equation, the earlier equation, that is equation where the then this becomes equal to the Sn is equal to L plus summation of the 3 term corresponding to x direction, that is L sigma x plus m sigma y x plus n sigma z x plus m multiplied by the summation of the term like L sigma xy plus m sigma y plus n sigma zy plus n multiplied by the terms 3 term summation, that is L sigma xy plus m sigma yz plus n sigma z, or simply it can be written then, that is Sn becomes L square sigma x plus m square sigma y plus n square sigma z plus 2 times of the if you put, so that becomes L m sigma xy plus m n sigma yz plus n L sigma xy, and this is what has been shown here in equation 21. The shear stress, that is SS, can be then simply evaluated as SS square, which is equal to total stress square minus normal stress square, or simply it can be written as or we can simply say that the shear stress component is equal to the summation of the x shear stress total is at x square plus y square and minus n. So these equations 17 to 22 we used to get this as undefined plane when the state of stress at a point is known. So corresponding to the LMN as, and one can represent it as L1, L2, L3, and then one can write in tensorial notation equation number 22 very simple form total is J can be 1, 2, 3. So Li and sigma ij. So this equation number is the tensorial notation stress. And let us take the case and resolve the stress in the normal to the plane AYZ, and therefore the one can see the total stress normal and shear stress is 0, suppose on to the plane ABC if you take. So the principal plane with normal direction as a principal direction with where the total stress is equal to normal stress as the principal stress. So the direction cosine of total stress can be written as, that is S capital Sx as Ls, pi component is Ms, and Z as this one. So equation 17, 18 and 19 can now give set of 3 equations as which has been shown in equation 25. That means L sigma x minus capital S plus m sigma yx plus n sigma xz is equal to 0, and L sigma xy plus m sigma y minus s plus n sigma zy is equal to 0, and L sigma xz plus m sigma yz plus n sigma z minus capital S, and that is what is equal to 0. Again, if we replace L, M, N by that is L1, L2 and L3, so this equation 25 can be further written in the tensorial form, tensorial notation, as Li multiplied by sigma ij minus delta ij, that is chronicle delta ij capital S, and that is what is equal to 0. So as you know, the chronicle delta ij becomes equal to 1 when I and j is equal, and it becomes equal to 0 when I and j is not equal. That means the equation 25 to have a non-trivial solution for the direction cosines L, M, N, the determinant of the coefficient must be 0, and that means the determinant, this particular determinant which is shown by equation 27, is equal to 0. These 9 component, the diagonal component I can tell. So the diagonal components of this determinant is sigma x minus capital S, sigma y minus capital S, sigma z minus capital Z, and other components are as the stress components are there. So expanding the determinant and rearranging the terms, we get a equation which has got the cubic terms of the total stress, square term, and the term containing capital S, and constant term. That means there are 4 major terms. So that means the equation becomes as s cube minus sigma x plus sigma y plus sigma z and capital S square minus sigma xy square plus sigma yz square plus sigma zx square minus sigma x sigma y minus sigma y sigma z minus sigma z sigma x and multiplied by capital S, and minus of the constant the other term that is having 6 more term like sigma x sigma y sigma z plus twice sigma xy sigma yz sigma zx minus sigma x sigma y x square yz square minus sigma y sigma zx square minus sigma z sigma xy square, and that is what these summations is equal to 0. So this is a equation, and the same can also be written as what has been shown here in equation 28, and that is simply a s cube minus I1 s square minus I2 s minus I3 is equal to 0, and where you are aware that I1, I2 and I3s are the invariants. So the I1, as you if you recall back, is equal to sigma x plus sigma y plus sigma z. I2 is sigma square xy plus sigma square y sigma yz square plus sigma zx square minus sigma x sigma y plus sigma y sigma z plus sigma x sigma x sigma z sigma x, and I3 becomes your sigma x sigma y sigma z plus 2 times of the sigma xy sigma yz sigma zx minus sigma x sigma yz square plus sigma y sigma z x square plus sigma z sigma xy square. So this equation 28 has 3 real roots. As you can see, the equation is in third order cubic equation, so therefore it has 3 real roots, which are the principal stresses sigma 1, sigma 2 and sigma 3 corresponding to this stress system. I1, I2, I3s are called the invariants as the first, second and third invariants of the stress tensor. These are in fact non-varying quantities since they are independent of the direction of the axis chosen. Suppose instead of x, y, z, the axis is taken as x star, y star and z star, then the equation 28 in terms of I1, I2 and I3 will have to be defined in terms of, that means sigma x star, sigma y star, sigma z square, and sigma xy star, etc. And the stress invariants corresponding to the new set of the axis can be then evaluated, which has been shown here in equation 29. You please note that now the I1, I2 and I3 as given above is replaced by the star terms, and the I3 is to be noted. So I3 becomes equal to sigma x star, sigma y star, sigma z square minus 2 times sigma xy star, sigma yz star, sigma zx star minus sigma x star, sigma yz square star plus sigma y star, sigma zx star square plus sigma z star, sigma xy star square. So if the three principal stress directions are chosen as the coordinate axis, then these invariants will become as I1, which is equal to I1 plus I2 plus I3. I2 becomes equal to minus sigma 1 sigma 2 plus sigma 2 sigma 3 plus sigma 3 sigma 1, and I3 becomes equal to sigma 1 sigma 2 sigma 3. Because shear stresses are 0, thus the invariants being three independent quantities and can be evaluated if sigma x, sigma y, sigma z, sigma xy, etc. are sigma star, sigma y star, sigma z star, sigma xy star, etc. are sigma 1, sigma 2, sigma 3 are known. Alternatively, sigma 1, sigma 2, sigma 3 can also be evaluated if L1, L2, L3s are known. So, in tensor notation, these invariants can be simplified and can be written what has been shown here in equation 31, 32 and 33. That means sigma 1 is equal to sigma II, that is the tensor. Sigma 2 is equal to 1 by 2 sigma ij, sigma ij, and invariant I3 is 1 by 3 sigma ij, sigma jk, sigma ki. So this is what has been the portion related to the stress, state of the stress, and the situations when we come across to change of the axis. All these things has been covered, and hopefully you will revise these things so that we can meet again in the next lecture, that is lecture 10. So thank you very much once again.